Anyway, I'm Helena Edelson. I am a principal engineer at Lightbend and a member of the Akka team. I recently joined, but I've been at Apple and CrowdStrike and basically been a platform infrastructure engineer working on data processing and data platforms. And so I kind of wanted to talk about, first of all, who uses Akka here or is familiar? Excellent. And how many of you are Scala or Java or other? OK, thanks. Yeah, I just wanted to know, I have some kind of introductory slides, and I didn't know if I should sort of glance over them for you guys or, you know. So I will cover some things, so thanks for your patience ahead of time for things that you already know. I kind of wanted to give a story of something that I recently noticed, also based on some of the work my colleagues are doing. Because I saw that there's so many similarities in what we have with Akka. Not everyone, myself included, before really joining the team, because I had written a lot of stuff like sharding. We had certain sharding patterns we had restrictions on, so we had written our own sharding and not used, for example, the Akka Cluster sharding. And now looking at it, you know, I'm able to say, like, hey, you know, there's these other patterns. We can perhaps make things more usable for accommodating these. And seeing all of these things that Akka has, people just think of it as a concurrency framework abstraction, or wonder why you would ever want to use actors in the first place. But looking now at what's happening with serverless and with Knative, there's a lot that we see that Akka has that it could fill some gaps and be really useful. So we've been looking into that, and we have a research project. And at the end, because I'll be going through these slides really quickly, I have links for things at the end. I'll give you my email, and I'm also available. You can find me on Twitter. And I'll post the slide deck on SpeakerDeck so you can look at the links and you can reach me directly or find me for the rest of the conference. I'll be around if you have questions, like, what were you talking about? OK, so this is a term that a friend of mine mentioned, and I thought it was really great. He's a Java developer and went to a meetup in Salt Lake City. And this was a few years ago, someone from, I think it was then TypeSafe, I don't know, came and gave a talk and was talking about the actor model and concurrency and asynchronous and just using a lot of words that him being a Spring developer, it just, you know, he had no context to hang this stuff on and really sort of grep what the guy was talking about. And I saw that as kind of an interesting problem. And I used to do these talks and use a lot of these, you know, buzzwords and everything, and now I really hate buzzwords. They just seem very markety. And I also realized we're all talking about the same thing with different words coming from data streaming, processing, and coming from, you know, enterprise engineers working on event sourcing. It's all really sort of all the boundaries are breaking down now, which I think is a really cool thing. But we use all these terms, and it's kind of silly. But I'm going to actually, unfortunately, in creating this talk, I realized I was doing exactly that, just using all these words, so apologize. OK, so things have been changing really rapidly in the last 5 to 10 years, specifically the last 5 years, with how we need to, basically because of all of the data that we're processing, everyone is processing data. I mean, it's not just that you have people in analytics anymore, which I used to do, handling the problems of data infrastructure and storage, and how are we going to store everything, and you do backup, and what about cold storage, and are we going to use a columnar store, are we going to use you know, a blob store, just all the things you have to think about, and how much it's going to cost, and what does your staff know how to do. Everyone has to deal with this stuff now, so it's really nice that you have things like serverless available where it can abstract a lot of that for you, but there are some challenges there. It's things that we can definitely improve or add to it. And one of the things that I think, the reason I want to start off talking a little bit about the actor model, first of all, it's 10 years since Akka was started, so we're having kind of an Akka-versary. So I thought it'd be kind of cool to just start talking about that a little bit, because I don't really like to just talk about a technology without kind of giving a reason why I would even bring it up. But there's particular things about the actor model that make it really useful, and I think now it's becoming even more relevant. So for example, it's been around for a really long time, obviously. A lot of the technologies that people bring up now, these buzzwords, people think that they're a new thing, especially if you pay attention to what the analysts are saying. None of this stuff is new, and I have a few slides talking about that. So it all started back for the actor model in the 70s and 80s with Carl Hewitt's paper on the actor model, and then Pat Helen and Jim Gray and Joe Armstrong working with Erlang, and a lot of what Akka was built on, a lot of those concepts came from Erlang. And what I thought was really interesting, because I have a biology background, is I've studied a lot about complex adaptive systems, and some of the concepts behind that, and that's kind of systemic organization, and not just complex adaptive systems and systems theory, which went into some of the early concepts and development towards machine learning and AI, but also with multi-agent systems. And these have been around and been academically researched and brought theoretically and developed into industry for, 20, 40 years. I mean, they've been around for a very long time, and some of these share a lot of commonality with actors and actor systems in the actor model. Basically, it's sort of disseminating out these entities, these autonomous processes that you're running, where they can communicate by some kind of protocol. It allows everything to be much more parallelized. Things can happen concurrently, and they can scale up and scale down. You can take out 100 of them, and the system is still processing. So for fault tolerance, it's very strong. And this slide just kind of gives you a quick example of complex adaptive systems. What they focus on is that asynchronous nature of the systems and of the entities in the system, how everything is unpredictable, which is what we deal with in distributed systems. It's nonlinear, adaptive, and versatile. So just a quick, again, I'm going to sort of glaze through some of the initial actor stuff, since a lot of you are already familiar with it. But actors, you have these actors, and they can communicate with each other by passing messages. It's always been this sort of event streaming model that they do. And there's also the innate hierarchy and structure of the actors in the system, which is why it is enabled to be much more fault tolerant, because normally if you're just writing something in, I was going to say a Spring application, but I used to work at SpringSource, but I haven't really followed what they've been doing lately, so I don't know. But if you're just going to write a service, just a plain service, you have to do all of the thinking of fault tolerance yourself. You have to build in a whole layer of fault tolerance and error handling with application errors and failures in the network. And so what Akka actually gives you is a very easy API to customize pretty granularly how you want those failures to be handled and by who. It could be handled by the actor that's actually thrown an exception. It could be handled, bubbled up to any number of parents in the hierarchy, something that actually knows what to do with that error or knows in the larger sense what to do with it. So it's really great in that way. And then the lower picture also sort of shows you how things are much more addressable, where normally, for example, in a serverless environment, you can't speak point-to-point, but Akka innately knows how to do that. It'll always know on another node, I need to speak to not just this node or a router on that node. I need to actually speak to a particular actor, or even in another data center. Akka can do that. And yeah, just a quick slide on multi-DC and distributed Akka usage, where you have separate JVMs, you have two different actor systems, and they can all communicate with each other very directly or indirectly. And it's extremely elastic. So also actors happen to be, it's baked into the system, like I said, that they're addressable. They're stateful. you can not only are you able to save the state from the messages that are sent to the actor, which I'll talk about, but they, in the way that they handle concurrency, it's all privately held, and so nothing can modify that. They're long-lived, they're not ephemeral, or things can be created just to work on a task and then shut down gracefully. And the way I see it, too, is I'm going to have a couple of these slides talking about different types of consistency versus availability, and a bit talking about the CAP theorem, but they allow sort of a much more, when you have these, a lot of operational complexity, you really have to balance what you're doing with all the choices that you can make with technologies, and it always depends on thinking about the total cost of ownership, what your particular use case is, what you already have, what your budget is, what your staff can do, what your DevOps team knows how to do. I mean, it's always very, there's a lot to consider there. Okay, so finding some kind of balance in all of this. Everything, like I said, we do now is about data. And not just that with our work, but everything is about data. Like your toothbrush has Bluetooth, your sprinkler system, you're checking the weather, you're entering what you ate that day in a log, everything we do. People are putting chips in their own bodies, so everything, everywhere has to do with data. And if you work in the industry, you're handling processing all of that data. And, wait. And this is the real important thing, is how do we deliver meaning from all of that? We have all these technical problems to solve, but ideally what we're trying to do for a business is deliver meaning out of that. And handling all of that, there's many different approaches. Again, it depends on what you're looking for, what your particular use cases are. But there are many ways to approach it, stream processing being one. And again, this is the word salad concept, where people call it stream processing. There's also event sourcing, CQRS. People get the terms mixed up. They're pretty buzzwordy at the moment. Or there's also, CDC. But they're really just all patterns of how are we going to approach data processing. And structuring data as a stream of events is not new. Things earlier on started with CEP, complex event processing. I think that was developed in 1989 or 1995 to 1995, sorry. Stream processing started in the mid-90s, came out of internet companies that had to deal with much more data than CEP was dealing with, which was really trying to do, look at causal event histories, which is a lot of what came in eventually to event sourcing. And event sourcing came from the domain-driven design, much more of the enterprise community. And sorry, I'm really thirsty. And then a lot of people confuse event sourcing with CQRS. They're quite different, but they just happen to use them together because they're very, that's one thing I really like to look at, is how some technologies are very collaborative, where if you put some of them together, they'll really help do a really solid solution for you. So event sourcing, really quickly, is looking at how your data, how your system is behaving, and trying to capture all the changes. So it's very good for sort of being able to have a forensics, where if you want to just be capturing the state as a stream of events, and then be able to store that in a mutable event log, and then for several different reasons, replay that and repair the state. And of course, you can, a lot of technologies do this, where you can save the data in snapshots with checkpoints, so that you can replay that from, there's definitely been use cases I've had to work on where I had to, we had a pipeline, we had to be able to replay data from, event 0, or you just want to do, from time A, a certain window of time A to time B. And event sourcing is really good when you need things to be auditable and need to preserve causality. And so some of the use cases for that would be cybersecurity, I've definitely done that. Banking, where you need to know where you are and how you got there. Click streams, seeing where someone just, how they get from A to B. Shopping carts, anything with a sequence of events that lead to, X, some point where something has to be preserved. And CQRS, how many of you are familiar with that? Good. So it's a pattern of decoupling the write path from the read path. And when I found out about CQRS, I thought it was really curious because by that time I'd been doing at least 4 years of data processing. And for enterprise development, it makes a lot of sense. But we were really already doing that in data processing, where you have the pipeline of ingestion of raw events data, everything being aggregated in the stream or in batch as it gets persisted. But then all the query side is completely different. It's different use cases, different teams. It would never really be the same data model. And so when you read things about CQRS, sometimes you'll see a bullet point that talks about, but you have to balance the complexity of having more complicated data models. Well, I mean, really, with the way everything is just converging with data processing in general and microservices, I think that's really not even an issue anymore. You would need to do that anyway. Plus, I think it's for decoupling reasons you wouldn't want that. So I kind of dusted off this, I thought this was funny, this old diagram that I showed during a Kafka Summit presentation I did. And so this was real-time bidding use case that I was working on. And I mean, it's old, so definitely some things to laugh about, particularly my ability to do diagrams. But it shows what this is really dealing with. On the green, all of these event emitters, they needed to be able to store 700 terabytes a day of data. And so basically, everything had to come in through the system. We designed it to come in through Kafka to handle the load and come into the microservices that we were building them in Akka. And they were all for fault tolerance reasons, many other reasons. And then we would do all the initial ingestion pathway processing of the data, store the raw data for event sourcing reasons, basically, and store pre-aggregated data from the raw data, and things with the TTL so they'd expire and move off to cold storage after that, all that good stuff. But then you'd also have, on the far right, where you have your ad hoc querying, or you have particular streams using Spark or Flink or whatever kind of processing that you wanted to do for your analytics, et cetera. That's all different data models. So I think this whole conversation about that is really interesting, particularly because it's converging and the write path is absolutely separate from the read for good reason. So here's where I get on like a pedestal. And, I don't really think it matters what you call it. Everyone wants to have these buzzwords and use some, which unfortunately I'm doing in this talk. I can't believe it. But it really doesn't matter because everything really is converging. No matter what, whether I'm a microservices developer or working on a data platform, I still have to ingest a ton of data constantly. Or with a lot of event spikes, I still have to write the raw data. I still have to, everything I just talked about in that really old slide. I have to not lose any data. I have to be sure that my team can handle the infrastructure choices that we're making. So I think, honestly, buzzwords are for analysts, and the boundaries between microservices and stream processing are gone. Or at least getting there. And really what we're seeing, and we have been seeing for the last few years, slowly is this convergence of microservices and big data. And you can think of the event stream itself as a replication fabric. It's already, this communication layer in a way. It's already this, a command layer with event sourcing, for example, in CQRS. But Akka persistence, so I started talking about Akka and actors a little bit. Now I want to get into some of the components that are built on top of that where if you can leverage a lot of these things, it's amazing how applicable they are to some of the things that we're trying to solve, particularly just because of because of the actor model. So they enable, Akka persistence enables stateful actors, where for a long time you would just be message passing, having an event stream with Akka, but they weren't ever persistent. And you would have to, I've done it for years, rolling your own for persisting data to Cassandra or whatever storage or temporary storage that you had. But so with Akka persistence, it's a really nice API to allow us to persist the state as the messages come in. So again, we're preserving that causality of what happens, how did I get, where am I now in the system, and how did we get there in the first place, so that I can replay that. It has also at least one message delivery guarantees. We have the ability, you can enable or disable if you wanted to use snapshotting. You can obviously be able to configure the size of the snapshots and tell the system very easily, like when I replay, I just want to replay from this time window to this point. And there's a lot of different storage plugins. Some of them are from the team, some of them are from the community. We welcome as many others that we can get to make the system much more usable by people. But there's already a Cassandra, Redis, DynamoDB, Couchbase, MongoDB, Hazelcast, JDBC, and there's quite a few more, actually. And then Akka persistence comes with some built-in ones. So that is kind of the event sourcing CQRS part of it, or event sourcing part of it. And people, I find, when they talk about event sourcing and the replay portion, they're really only thinking about the enterprise part of it. So because I have a big data background, I always think about what we had to deal with was, it wasn't just on failure, I want to replay and get back to the state. I have algorithms, my machine learning algorithms or my analytics algorithms. We needed to change them. Therefore, I need to replay against the historic data. Has nothing to do with failure. We just want to, somewhere in our system, eventually cold storage, have those raw events. Typically, that's the scenario where you need those raw events, not the pre-aggregated data for queries, faster queries later. And so I need to be able to replay that raw data. But for more microservices and failure reasons, you would have the standard things, this is one thing that's really difficult, is handling rolling upgrades, rolling restarts, when your infrastructure decides, okay, we have a maintenance window, we're going to systematically shut some things down and start them back up. If you're an application that needs state, that's going to be pretty difficult to reason about and solve, and you're going to end up needing to write a lot of code to handle that. So back in the day, that's just not fun at all. It takes a lot of time. So other things with just network issues, when you have network failures or application errors, that's when you would have to handle it. And one of the things that Akka does very nicely in its actor supervision is, like I said before, when there's a failure, the supervisor, if you configure it that way, will restart the actor. So if something is restarted, if it's not a persistent actor, it will restart it, and based on what you tell it to do, replay to catch up, to rebuild that state. And general failure and recovery, so Akka out of the box gives you a lot of these, the failure awareness, sort of all these different life cycle hooks. And people don't really talk about that very much, but I use that all the time. Before a service starts, that you can, every time you need to subscribe to something, you can do it every time it restarts. So there's all this being able to plan the whole behavior of your systems that I think are missing in a lot of frameworks. And I really appreciate that. So I just want to start talking a little bit about Aqua Cluster and then get into a lot of the components on top of that let us think about things like distributed data. Different parts of Aqua Cluster are the cluster Singleton. If you need one thing to be available, one service to be making a decision on all the nodes in the cluster. Distributed data, cluster sharding, We have a split brain resolver for partitions. We have a new distributed lock for Kubernetes. It could be extended for anything else, but right now we have it implemented for Kubernetes, and multi-DC. We also have a whole Akka management for cluster bootstrapping, which is really useful for Kubernetes, and service discovery. So that's all just open source stuff that you can grab and use anytime. OK, so just to quickly get into just the basics of Akka Cluster, if you're not that familiar with it, and I'll go pretty quickly because it seems like you guys are. So Akka Cluster, quick premise. It's a decentralized peer-to-peer communication where I have a cluster of nodes, and I can partition them by particular roles, where I have some roles, and that could be service A, some could be service B. And they can all communicate through Gossip protocol. There's a whole cluster membership service that I'll talk about, failure detectors, all the self-healing and coordinated shutdown that it has. So really quickly, just probably the most useful parts of the cluster API, where you would say, what's your self-address, what data center are you in, what are my roles on a particular node. I want to do a command if I want to join. I want to register to do some kind of function on a certain member up or on member removed, do some action. You can subscribe to two different types of behavior of subscribing to any of the cluster events. Also, you can unsubscribe, leave the cluster. You can down yourself or another node. So there's a lot of control you have in just this very simple API for the cluster. And cluster communication, each node keeps track of a few nodes through the failure detector. Periodically, it's going to be gossiping to each other and doing a kind of convergence on it. The way that it really works behind the covers is it'll be sending out heartbeats, and all of those heartbeats, it's important actually to tune that because every system is going to behave differently, every network is going to behave differently, and so you can see quite a difference in the cluster behavior based on what you tune the heartbeats and the failure detector to. You can also customize the failure detector, which I think is a really interesting thing to do. And the way that works is as it's doing the heartbeats and as the gossip is going around to the different nodes. If one of the nodes is detected here, we say member 3, and each one has a unique UID, each node. If it detects that one of them is unreachable, it will be watching for that. The failure detector notes that, and it gets gossiped around to the other nodes. And then note that it's unreachable, and then when it becomes reachable again, it can rejoin the cluster. There's a lot of subtleties to that I won't get into. There's a lot of cluster events that you can subscribe to. There's the root one, the cluster domain event, but you can be aware of when members are up or particular members are up so that you can take some action. When things are unreachable or a member is removed or any of the leader events or reachability events. And the cluster state is really interesting. That's what you would be able to receive that when the node first comes up. And you can get a lot of information on the state of the cluster right there for any kind of intelligence that you might need to do. And usually you would subscribe to things right when you join the cluster. So the gossip protocol, the cluster membership used in Akka is based on Amazon's Dynamo system. And the particular approach was taken in Basho's RAC, distributed database. And so it's just a gossip protocol being gossiped around to each of the nodes. And it's communicated through this protocol so that members, there's also a vector clock, so you also know which version you're looking at. And eventually there's going to be a gossip convergence. And the gossip is, the cluster state is basically a CRDT, which I'm going to talk about shortly. And that can be deterministically merged. The cluster leader, people get this confused a lot. There's no leader election. It's a masterless cluster leader. There's, the role of the leader is basically only to modify who can change their status in the cluster, so joining to up or exiting to be removed. And each of the leader decisions are based on the local data center that it's in. I'm going kind of fast because I have a ton of slides for you. So the cluster leader, just on a particular node, it'll know that it's the leader, and the other nodes in the cluster will eventually know who the leader is and who's up, who's down, all of the state of each of the nodes. And like I said, you can have cluster roles, very easily configurable. And the cluster membership state, so this is just the graph of walking through from the join to when a node is up, when a node can, it can be a user action when you can bring a node down, or when it's leaving more gracefully, exiting, and then when it's removed. And really quickly, just about the member node life cycle. This is sort of the happy path, joining up, leaving, et cetera. And then when they become unreachable, down. But when that happens, they can be brought back up again, like if there's a network partition and that heals. And so with network partition, it's amazing to me, actually, since I started working with the split brain more recently, I'm surprised at how often these happen, network partitions. And I think it's because a lot of systems just are not aware, like even ops teams will not quite be aware that network partitions have occurred. And so we'll actually find out about them happening quite a lot. And I've seen this quite a bit happen where the dev teams are the ones that have the evidence that network partitioning are happening because of that, and also like slow network behavior because of the heartbeats and the failure detector that the ops teams won't be aware of, and I think that's pretty curious. So when a network partition happens, you might have a cluster and they get separated off, and then all of a sudden, they think that they're two separate clusters, and one of them thinks they're the leader on one side, and the other thinks that they're the leader. So you have two cluster states happening. One of them, says, these two, member 3 and 4 or 3 and 5 are unreachable, and then the other 3 they think are unreachable for the other cluster. And then eventually, because after a certain period of time, a configurable amount of time, they realize they just call them down because they haven't had any heartbeats from them because of the partition. And so what the split brain resolver does, and there are some open source versions, this is commercial support, but it has a few different SBR strategies. It's the static quorum, keep majority, keep oldest, keep referee, and down all. Down all, for example, would be if you've got really bad network problems and you just need to retain your consistency. And I have a link there. I have a link, I think, on a lot of these slides to the documentation if you wanted to read some more. So for example, I just wanted to give a quick example of one of them, because there's not much time, but the keep majority is basically where you would designate, so if you have a 5-node cluster here, we want to keep the majority, so that's going to be the one that becomes the one that isn't downed, basically. It's all very configurable, pretty easily configurable. And the cluster singleton is the next one I wanted to talk about. Very often I've found you need one node in an entire cluster to do one thing or to make certain decisions. And that's when you would use a cluster singleton. You have to be careful at the same time, because once you have something that's a coordinator or one thing, you all of a sudden introduce a single point of failure, which is exactly what Akka tries not to do. Or doesn't, except for something like this. But it's really useful, just an out-of-the-box dependency to add to have one thing doing that behavior. And the way that it's structured, for example, if you have 3 nodes here, and then I have on each of the nodes gets deployed a instance of the cluster singleton manager. And then you're going to talk to this cluster singleton proxy that knows how to route to the actual singleton actor on the node that it's on. So for example, when you're sending a message, it's going to route through the proxy, and the cluster singleton is going to know how to route it to the singleton actor. And then OK, failures next. This is what it looks like just to configure it with, we're in an actor, and we say actor of, and I want to create a Singleton manager. So you can give it, there's quite a lot of configuration that you can tune things with. You can also say, I want this Singleton to only be related to a certain cluster role. And then you configure the proxy, and then you can just talk to the proxy, and the proxy is all you need to get to any node that that one instance of the Singleton actor is on. So that even in a failure, if the Singleton before was on that top node, it's going to be brought back up in a process of handover, basically, where it's going to be brought back up on another one of the cluster nodes, and you're still sending, and it's that location transparency that actors have, where you don't need to know, Akka itself knows how to route to that node specifically. And the cluster singleton is one of the ways that we can guarantee more on the strong consistency side. But primarily, Akka actor, the framework alone, is more about availability. And so these are really how we start to build in more of a consistency model. So distributed data, and I wanted to talk a bit about CRDTs and eventual consistency. Promise I'm not going to show you a cap diagram, though. I was tempted. So what this is really about is partition and delay tolerant data availability with it. Like Akka distributed data is a multi-master replication in memory. So it's basically designed to allow sharing between cluster nodes. And what it does, well, first, just talk about CRDTs. It's an approach, one of many approaches to eventual distributed consistency. We replicate data across the network, first locally. The concurrent updates from different nodes, it doesn't need external coordination, so it's much faster. Updates execute immediately. They're unaffected by network outages, network faults. And it basically allows consistency without consensus. So it's obviously limited in what you're going to want to use it for, because there are definitely use cases where you absolutely need strong consistency, and you can tolerate things being slower. And then there's some, particular use cases where you would rather have things be faster, more available, and more scalable. So you really have to think about what your use case is when you're thinking about this. So the application of CRDTs, basically, it's a replicated counter, one example, which will converge because of it has increment only or increment decrement operations that commute. And that's based on the mathematical premise. So you could have things like service discovery, shopping carts, where you're doing data aggregation. Actually, a really classic example is collaborative text editing. And this is not a new idea. I don't know why, but it always bothers me when people are like, oh, this is a new thing, and people have been doing it for like decades. It's not new, so I listed a whole bunch of papers starting in 1976, a lot of research papers on where all this stuff came from with CRDTs. And so Akka distributed data is built on CRDTs, replicated in-memory data store, using state-based CRDTs, so CVRDTs, where it's low latency and high availability, where you have much more granular control over the consistency level between reads and writes. It's very easy to configure that. And the API is like a key value store. And there's several different primary types for CRDTs themselves. There's counters, registers, sets, maps, and graphs, like a DAG, distributed DAGs. And what we have with Akka distributed data, we have, because we focus only on the state-based, but we have the operation based in the multi-DC persistence. The state-based are where you're just sending across the network the delta, so just the change. So it's much faster. You're not taking up a lot of network resources while you do it, and it eventually gets merged. Each of the particular data types has to implement a merge function. So the G counter, G set, PN counter, like a positive negative counter. And these are all out of the box. And then it's very easy to also implement your own. I think I have a sample for that, actually. And it's built with a replicator. So the replicator gets deployed to each of the cluster nodes. And while it's doing the operations, it's saving it to the local store, and then it gets asynchronously gossiped around. So the API is pretty simple. It's just an update where everything works for the routing by a unique key. And so there's an update with the distributed data or with the delta, depending on the type. You can do reads, you can subscribe, and you can delete. And so I have a couple of code samples that you can actually read. So here, sorry for anyone not doing Scala. It's just using the distributed data module, creating the replicator. You can pick what kind of write consistency you want for, what I really like is I can be doing a particular operation and set the consistency, the write or the read consistency on that specifically. So when something sends me some kind of command to increment something, just a simple operation, and I just sent the replicator an update with the key, what kind of data type I'm using here. I'm using a PN counter, and then I can optionally pass in some kind of a request, some kind of context that when it comes back, whatever the result is going to be, whether it was successful or not, I can use that in my logic. And then at the end, that kind of weird thing at the very end of that line is what your function would be. What's the actual operation you want to do there? And so you would either get things like an update success, this is the API, or you can get an update timeout. I'm going to go into that in a second. And this is the trait, the base trait, the replicated data, where if you did want to create your own, you can. So I have this device event, for example, where I just have to implement, the type, and then override, do some kind of implementation of the merge function. And so the write consistency and the read consistency, the fastest, obviously, is where you're going to write and read to local, and then it does the asynchronous work in the background. You can write to n number of nodes and call that good, and then it'll eventually propagate around to all of them. Or you could say write majority or write all, of course, being the strongest consistency, highest latency, and the lowest availability of all of them. So you really have to tune it for your particular use case. So I have a small capacity tracker example where some of the stuff is a bit boilerplate. You would obviously have it in some kind of common nodes, but I just wanted you to be able to see what I'm including in there. So the basic setup, I set up my write consistency, I set up what the key is going to be, and then if someone says, oh, the capacity has been reached, because there's some capacity service is telling me and giving me some ID on that, then I can send to the replicator all of the nodes I want to replicate around and update that the capacity has changed. And here I'm using this CRDT, the flag, where it's just a Boolean flag, and I can say, this particular ID, the capacity for this has been reached. Just a very simple example, but you can see what you can do with that, I think, from there. And then the update success, failure, and timeout. Success is good to go. Failure is just going to say, I think, that's where you've completely failed, and do whatever kind of handling you need to compensate for that. And update timeout, for example, if I said I'm going to write to 3 nodes and then let it happen in whatever time after that, update timeout just means that it hasn't written to those 3 nodes within our configured timeout. And again, everything is tunable. And this is how you would subscribe to some of these events. So I just have like a CDC actor, something doing change data capture. and I want to know when something like that's happened. So I'm just subscribing. I've got this particular data key that I'm subscribing to. Self is just that instance of the actor subscribing to changes. So when I get this replicator changed with this particular data key that I've subscribed to and the flag, I can just say get of the entries for that particular key, and I can see that the capacity has been reached, it's been disabled, and then I want to take some further action downstream in my system. And it also has configurable durable storage. So while it's in memory, by default, there's also, out of the box, you can use local disk. It uses LMDB, but you can also use some kind of other durable store with it. And again, distributed data, what that brings us to more is the always available, but it does give us consistency as well. And again, I think I sort of alluded to this, is that there's particular use cases where you would not, where it's a really good fit, like something simple like the counter or the flag, or tracking a map, a state in a map. But it's not designed for, because it keeps a lot in memory. At a certain point, if you're doing actual big data, it's not a good fit for it. Data is held in memory, and if you're not using a delta CRDT, where you're just passing the change versus the whole event, which is the state-based CRDTs, then you're going to be propagating that state around, and in those use cases, it's not the right fit. Or when you need high consistency in some kind of financial use cases, for example. Cluster sharding, I think, is the last cluster module I wanted to talk about before getting into sort of the end conversation. I don't know how much time I have, though. How much time do I have? Oh. So let me skip cluster sharding. Can I do like 1 more minute? Oh, did you give me the 10 and I? That's because I'm small. Couldn't see you. All right. I'm going to post this. You can see about cluster sharding, which is actually really cool. I was looking forward to that. Let me scan through that really quickly. Serverless. I'm going to talk about this in 60 seconds. Ready? So I think you all know what serverless is. I'm going to skip right by that. Some of the things, like I mentioned in the very beginning, about function as a service that we noticed, where it's really great. It's a really great start, but there's some things like not it being so ephemeral, it taking so long for services to start up. Every time they start up, it's great for shipping the data around, but if you're dealing with things that need state, it's very difficult. I worked recently at a company where we were basically building a serverless platform, and because I was on the platform team, I think we very quickly ran into problems with things where we had to deal with state. And all of the users were expected to have these stateless operations. And it was very interesting trying to resolve that. So it's definitely something to think about. I'm going to skip this stuff. My other 30 seconds. So if you're dealing with more complex business use cases where people typically would go to a database, or they need some way for the message out processing to produce the message out, you would need to have some kind of state management. And so some of the limitations with serverless, like they handle only one event source, all that computational context is lost when it goes down. They're expensive to load and store state. Some of those things, that addressability, a lot of that is sort of innate in Akka, we realized. And so we've been doing some R&D work, and we'd love anyone else to get involved. I'll show you the links real quick. I am almost done. So with Knative, Akka Cluster, and some of those components that I talked about very quickly, gRPC and CRDTs, where we have the message in between the user function and the message out, and we also have state in and state out that we're doing the way that we're looking at it at the moment is with using event sourcing, where we have our commands, our applies out, and the event log in and the event log out, and with CRDTs, where we're doing the state or the deltas in and the deltas out. So serving stateful functions, just 2 more slides. I'll get to the good part. So we have our user functions. This is a basic architecture that we're looking at with Knative stateful serverless, where you're emitting events to Knative events that to be able to be consumed by the read sides. And then we are doing it with Akka Cluster sidecars in Knative. And I just want to show you one more thing. So the repo is the GitHub repo, if you want to take a look. And then there's also, I think that's the video, the stateful serverless. Please take a look at that, and we'd love people to get involved. It's kind of a really interesting project to see how we can possibly make it a lot easier for these other they're not edge cases though, these other cases to be able to work with serverless and functions as a service and still have some kind of state that you're working with. So I have a lot of links. I'm going to post this on SlideShare. I'm going to tweet it. If you want to check my Twitter, I'll tweet the slide deck soon after the talk. And thank you so much. Sorry for the rushing through everything.